Let's get it going here. Welcome back, everybody. I hope you're all safely home and had a good little break. I had a good little break. I have graded all the tests from before the break, so you should be able to see your grade on Gradescope. And as usual, I put comments in Gradescope on next to each of your answers. If those aren't good enough, or if you want to, just go over things that didn't work out for you, I would be happy to talk about it. So please let me know, and we can chat about your test in particular. There was also, I also wrote out my answers and put them on our class website by the homework assignments. So you can check that out too if you don't want to talk to me about it, but you want to know, what I was expecting for the answers. You got them. All right. Any questions about the test? No, of course not. Good. We have only 2 weeks of normal class left, so we're gonna have a homework and a quiz this week, and a homework and a quiz next week. I'm sure you've all heard by now that there is a new option to go pass-fail for your courses. If you're wondering about what your grade is so far to help you make that decision, I would be happy to tell you. Just send me an email, and I will tell you what your grades are as of now. Or you could probably figure them out yourself, but I don't mind doing it for you. I just look in my spreadsheet. All right. Any questions about any of that? Any business? All right, great. So we are this week talking about the definite integral, and I thought I would do some examples concerning the definite integral. So the definite integral is also known as the area under the curve. The definite integral is very different from the indefinite integral, which is the integral we were doing last, on the test or a week ago, which is about the antiderivative, right? That's called the indefinite integral. The definite integral is quite different. In particular, the definite integral is a number. It's not a function. Like the antiderivative, the indefinite integral gives you a function as the answer with a plus c on it. But the definite integral is something totally different. And now actually there is a relationship between the two, which is why they're both called integral, but as of now we haven't talked about that. So the definite integral, what it represents is, like for example, the integral, you write it as an integral, but it has these two numbers on it. Say the integral 1 to 4 of x squared dx. This means this area, you look at that function x squared, the graph of that, and then the 1 and the 4 refer to looking at the range of x values from 1 to 4 and taking this area. That's the meaning of the definite integral from 1 to 4 of x squared dx. You take that function, you take the you find the area under the curve, like between the x-axis and the curve, by some means. Like that's a weird shaped area, so it's not clear at all how you would ever figure out what the area is, but that's what the definite integral represents. It represents that area. Now, what we are talking about this week are various methods for estimating the area under the curve, and the estimates are all about, so one of them, the first class worth, estimates the area by drawing little rectangles like this, and then you add up the area of the rectangles. Now that's not exactly the same as the area of the curved shape, but at least it's something as an approximation to the area of the curved shape. And adding up the rectangles is easy to do, like geometrically, they're just rectangles, so it's not hard to find the area of the rectangles. All right, now there are several different variations on this basic strategy about the rectangles for us to discuss, but the rectangle height, of course, is always this delta x, which is this sort of small horizontal width of each rectangle. times the value, the height of each rectangle. And the height of each rectangle is given by plugging values into the function, because the heights are given by that curve. So it's always delta x times f of something goes in here, right? It's a different value you plug in each time, but each of these points here would be determined by plugging a value into the function. All right, let's just do some examples. I'm sure you know I explained all this in the video, and I don't need to say it again. This time is just for doing examples. So I really just have two big old examples to do. Number one, let's estimate the definite integral. The integral from 0 to 3 of 2x cubed plus 4 dx. Using, and there are several different strategies that you saw in the video, so I'm going to do A, B, C, D, E. Sorry, I need to say, for all these parts, I'm going to say using n equals 6. And the different n equals 6 refers to drawing 6 different rectangles or different whatever, so you can use other shapes too in some of these methods. Part A, using the right endpoints. Part B, using the left endpoints. Part C, using the midpoints. Part D, using trapezoids. Called the Trapezoid Rule, and Part E using what they call Simpsons Rule. Simpsons Rule. All right. A, B, C, D, E. They all have very similar setup, but you just use slightly different formulas each time, and they give you different answers. They are all approximations of the area under the curve of this function, whatever that is. Now, that's a strange-looking function, I suppose, but you don't have to worry about what the function looks like. What you should worry about is subdividing the interval. So I am doing the interval is from 0 to 3, right? That's these numbers here, 0 and 3. And I said using n equals 6, that means you divide the interval up into 6 equal pieces. So I'm going to make a little sort of very simple little chart here for my interval from 0 to 3. And I need to divide this into 6 equal pieces. I suppose if I were, you know, cutting a cake or something, I would cut it in half once and then I guess do thirds here, right? And then you need to figure out what are those intermediate numbers there. Anybody think you know what is like this? I mean, obviously the leftmost one is 0. What about this one right here? Can someone shout it out? A half. Somebody said, yeah. Thank you. This usually you can just figure out sort of by common sense. It is if I take 0 to 3 and divide it into 6 equal parts, then the width of each little part will be a half. So this one, the leftmost point is 0.5, and then 1, and then 1.5, and then 2, and then 2.5, right? I'm always going to use decimals for these. It's easier, for me at least. If you are ever concerned about how exactly did I figure that out, I just said sort of by common sense, if you have 0 to 3 and divide into 6 pieces, the width of each is a half. If that common sense doesn't compute for you, you can always remember this formula. It's a good idea to remember this even if you feel like the common sense does work out. Delta x is b minus a over n. Delta x, remember, is this little width here. In this example, where the b and the a represent the two interval endpoints. So in this example, I would get 3 minus 0 divided by n, which is 6. N is the number of divisions you make. And I get a half, right? Which is what I said before by common sense. So if you can do that in your head by common sense, that's totally fine. If not, it's a good idea to remember this little formula for the delta x. Okay, anyway, for part A, I'm going to use the right endpoints. That means in part A, I'm going to consider of all of these little markings on the little interval there, I'm only considering the ones on the right of each little sub-interval, right? We divide it into a lot of bitty bits, and for part A, I'm considering only the endpoints on the right. And so for part A, what we do is plug each point in this case, it would be just the red ones that I picked there because I'm using the right endpoints. Plug each point and multiply by delta x each time, right? And so how we do, it's going to be just, so I'll say like A, that is the area. Well, it's not the area, it's the, I mean, it is the area of something. Can I just say it's the integral, 0 to 3, what is it? 2x cubed plus 4 dx is approximately equal to, I'm going to plug in each point to the function. That gives you the heights of the rectangles, and then you multiply each one by delta x, which gives you the width of the rectangle. So I get 1/2 times f of 1/2 plus 1/2 times f of 1 plus 1/2 times f of 1.5 plus blah, blah, blah. What I'm doing is I'm taking these red points up here, plugging each one into the function, f of each one, and then also every time multiplying times 1/2 because 1/2 is what the delta x is. All right, and then you keep on doing this. If you're doing this on a quiz or on a test, it's totally fine with me. If you write the ... you don't actually have to write every single one of them. If you're going to write the ... you better tell me where it and where you finish, because that's important going between these problems. I finished, the last one is f of 3. All right. Now, you shouldn't leave your answer like this because I don't want to see f's in your answer. Your answer is supposed to be a number. Now, I don't care if you actually plug these things into your calculator to get a specific number at the end, but I would like you to plug in, at least tell me that you know what f means. F means this function over here, right? Where you see f, that indicates that function on the inside. So my final answer is 1/2 times, and now I have to do f of 0.5, right? I'm plugging into the function. I go 2 times 0.5 cubed plus 4, right? That was f of 0.5. And then, next, 1/2, 2 times 1 cubed plus 4. Next, 1/2, 2 times 1.5 cubed plus 4. Is it cubed or squared? I think I wrote squared at the beginning. Sorry, no, it is cubed. All right. Losing my mind here. All right, and the last one is 1/2, 2 times 3 cubed plus 4. Squeezed it in there. All right. This, if you like, you could plug into your calculator. It's kind of a pain. There's a lot of stuff to type into your calculator. I don't care. On a test or something, I would expect you to just leave your answer like that. All right. Are there any questions about that one?
Is it okay if... Oh, sorry. Is it okay if we skip that step, like, in between the final answer?
Yeah, if you are doing these, if you really know what you're doing, you don't really need to write this step here. Is that what you meant? You can just, yeah, it's not so hard if you know what you're doing to just go straight to the answer.
Okay, thank you.
Yeah.
Do you have to put the 1/2 in front of everything? Like, can't you just put it on the outside?
Yeah. So I think I did this in the video actually. You can also write this. It's maybe a little simpler if you just factor the 1/2 out. Like at this step here, I have many things added together, which have a 1/2. Every one of them has a 1/2 in front of them. So if you prefer, you can write it this way: 1/2 times, and then all that other stuff. 2 times 0.5 cubed plus 4, plus 2 times 1 cubed plus 4, plus, etc. The last one. 2 times 3 cubed plus 4. Yeah, that's fine. Those are the same. I don't care which way you do it. Is that what you meant?
Yeah, thank you.
Great. Any other questions about that one? All right, this was using the right endpoints. What about, so that was part A, right? Part B said using the left endpoints. It's almost exactly the same. The only difference is up here, when you pick which points you're going to plug in, you use the ones on the left instead of the ones on the right. So part B is pretty much the same, only, I mean, I have the same interval, the same subdivisions, only this time I'm going to choose the endpoint on the left every time in each little subinterval. we choose the ones on the left. So this time I do include 0, but I do not include 3. Would you mind if I just jump to the final answer? I mean, it's exactly the same. The only difference is which points you include. So this time my answer will be 1/2. I'll do it this way with the factored out 1/2. I'm going to write all of this stuff again, only I will begin with 0 and I will end with 2.5. So it's 2 times 0 cubed plus 4 plus 2 times, the next one would be 0.5 cubed plus 4 plus blah, blah, blah. And the last one, 2 times 2.5 cubed plus 4. This is how we do it. That is the left endpoints. All right? If you've already done the right endpoints, you will be able to immediately write the answer for the left endpoints. Change the numbers around. Numbers. Any questions about that one?
Yeah, I have another question.
Yes.
So for each thing that you put inside the parentheses, why don't we put parentheses like for what we're plugging in?
You could, like this, you mean? Oops, not that one. Is that what you mean?
I like that.
Yes. You can do that. It's not wrong. It's not really necessary here because what I have there are many things all being added together. And when you have a bunch of stuff added together, you can put parentheses if you want to. Like if I have 1 plus 2 plus 3 plus 4, this is the same as 1 plus 2 plus 3 plus 4. So those parentheses, which I just inserted, are not necessary. They're not wrong. And it may seem more clearer to group them in this way because they do. I mean, these two things, they do kind of go together. Although if you were to omit the parentheses, you'll get the same answer anyway. Excellent questions. Thank you for your questions. All right, let's do part C. Part C was same thing, but using the midpoints. All right. We do the same thing, but using the midpoints. Okay, so the midpoints means you make the same divisions, but you choose the midpoints. The midpoints being these points here, right in the middle. All right. These, again, by some kind of common sense, you have to figure out what those midpoints are. Each one is just, in between, right in the middle. What's the leftmost midpoint going to be there?
0.25.
0.25, yeah, that's what half of 0.5 is. 0.25. And then I guess I have 0.75, 1.25, 1.75, all right? 2.25, 2.75 is the last one. And otherwise, we do exactly the same thing. So again, I think I can just jump straight to the answer if you don't mind. I got my 1/2, that's the delta x. The delta x is still 1/2. That still represents the width of each subinterval. And they're the same subintervals, they're the same widths as before. It's just a matter of which point I plug in, and this time I'm going to use the midpoint. So I go 2 times 0.25 cubed plus 4. And when you're doing the midpoints, use all of them. You don't skip the first one or the last one or whatever. You use all of them. Next is 2 times 0.75 cubed plus 4, etc. If you're going to do the dots, it's best usually to write at least 2 things at the beginning so you can see like what the pattern is, and then write the last one. The last one, 2 times 2.75 cubed plus 4. And this is how we do the midpoints. Any questions about that one? The midpoints. If you ever can't figure out what the midpoint is, in the worst case, you can take the average of the two numbers, right? Like this 1.75 here, it's the average of 1.5 and 2, which if you had to, you could compute by, add these numbers together and divide by 2. That would be the average. Okay, that was part C, the midpoints. All of those, A, B, C, they all represent using rectangles to find the to estimate the area under the curve. If you do plug those numbers into your calculator, you will find those 3 numbers from A, B, and C. They are different answers, but they should all be around the same. They should be approximately the same because that's the point of these are 3 different approximations of the true area under the curve. Part D and E are slightly fancier ways to estimate the area under the curve, although you'll see it's not harder to do in your particular example. They are just theoretically fancier methods. So we are using the same interval, 1, not 1, 0, 0.5, 1, 1.52, 2.53. Part D was the trapezoid rule. The idea behind this, like abstractly, is instead of drawing rectangles under the curve, you draw trapezoid shapes, which look like that. It's a much better approximation to the true area under the curve than rectangles. A rectangle will miss a lot of the curved region. The trapezoid will miss some of the curved region because you're drawing a flat line on top of these shapes while the curved region is not flat. But the amount of area you miss out from trapezoids is much smaller. Anyway, there is a special formula to use for the trapezoid rule, and this you just have to remember. Here it is. I will refresh your memory. You do b minus a over n, and then 1/2 f of x0. I'll tell you what I mean by this in a moment. F of x1 plus f of x2 plus blah, blah, blah. F of xn minus 1 plus 1/2 f of xn. So what the little x, x0, x1, x2 mean, this one is the leftmost endpoint, right? This is the rightmost endpoint, and all the other ones are in between. This formula, what's important about the formula is the b minus a over n out front, and then these 1/2s. All right. This is really very much like doing the right endpoint or the left endpoint rectangles, but this b minus a over n, of course, is the same as delta x on the outside. The only difference really is these 1/2s here, right? 1/2 here, 1/2 here, and you use all the points. Okay. When you're using this formula, you shouldn't like try to plug in for the n. It's really not. You'll confuse yourself about what does this mean? Xn minus 1. Xn means the rightmost point. Fn minus 1. Xn minus 1 means the one before that, right? This is the last one. This is like the second to last, or the next to last one. Anyway, let's do it. In this example, I'm going to plug in. What about b minus a over n? So we get, blue. We get b minus a over n out front is 1/2. If you want to plug in for all of those, it would be this, right? 3 minus 0 over 6, which of course is 1/2. And then I'm going to use the trapezoid formula. You put 1/2 on the first one, and then plug in as usual to the function. So it's 2 times 0 cubed plus 4. Remember, that's what our function was. Here, for all the haters out there, I am putting these parentheses here. These parentheses are important because you're trying to multiply it all by 1/2, and that matters. The other ones, the parentheses will not matter because they don't have coefficients in front of them. Next, I see f of x1. That would be 2 times 0.5 cubed plus 4. Next, 2 times 1 cubed plus 4, etc. Right? Those ones do not get halves on them. The last one does. I'm going to write the second to last one also, just so that you can see what the pattern is. 2 times 2.5 cubed plus 4, plus, finally, 1/2. Sorry, I'll put it on the same line. I can do this. Finally, 1/2. 2 times 3 cubed plus 4. And I got big parentheses like that. All right, this is the trapezoid rule. If you like, just to be safe, you could put them all in parentheses. I know some people are a little worried about, when do I need the parentheses? When do I not need the parentheses? You can put them in there. It doesn't hurt. The parentheses here are not really necessary. This one is because I got the 1/2 in front. This one is also because I got the 1/2 in front. Anyway, this is the answer for the trapezoid rule. Any questions about how I did that?
So just to clarify, we're basically plugging in like everything, the left endpoints, right endpoints, and everything in between.
That's right. Yep. And so the only thing special about the trapezoid rule is, first of all, you use all the points. You don't skip the first or skip the last or anything. And also, you insert these extra 1/2s. That's the only difference. You just have to remember where those extra 1/2 goes. If you're wondering, like, what does that have to do with trapezoids? Watch the video. I explain it. For now, I'm just telling you how to do it. Right. Excellent. Okay, that was part D. Part E, I had E also. And part E was Simpsons Rule. And this is yet another Simpsons Rule. Yet another strategy using different shapes. Rather than using trapezoids, you use weird sort of rectangular-based parabola shapes. It's a very strange concept. But it turns out the formula for doing Simpsons Rule is very simple and super accurate when you're doing this in terms of approximations. The Simpsons Rule is the most accurate of all of these approximations. Anyway, you have to remember Simpsons Rule has a formula that's a little weird, but not terribly weird. So first of all, the outside has b minus a over 3n. Why the 3? Well, it's complicated, but this is what it works out to be. And then the inside has no half there. It has a 4 on this second one, then a 2. And then in here, the coefficients, they alternate. 4, then 2, then 4, then 2, etc. All right? This is how Simpsons Rule works. You have no coefficient on the first one. Then the coefficients alternate. 4s, then 2s. Then the second to last one is always a 4. And then the very last one has no coefficient. This is strange, but this is the formula for Simpsons Rule. It turns out that this gives you a very accurate approximation of the true curved area under the curve. And this one only for n even. Because of the details of where this formula comes from, the formula only works when n is even. So when n is odd, you don't do Simpsons Rule. You only do Simpsons Rule when the n is even. All right, that's the formula. Any questions about the formula? I think we should just do the example. Let's just do it. So it's the same as all the other ones, but I use a slightly different formula. So in front, I go 3 minus 0 over 3 times 6. All right, that's this 3 right here is important. I put the 3 here, right? And then inside, when I'm adding everything up, I go 2 times 0 cubed plus 4. I put those parentheses for fun. Next, 4 times 2 times 0.5 cubed plus 4. 2 times 0.5 cubed plus 4. All right, I am putting coefficients 4, then 2, then 4, then 2. All the way down, I put the dot, 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 because I don't want to write all of them. The second to last term will be 4f of, the second to last was 2.5, right? 2 times 2.5 cubed plus 4. Sorry, I messed this up. I hope you noticed. This right here, I wrote the same thing twice, didn't I? I meant to write 1 in the second one there. So this should have been a 1. Sorry about that. Should have been a 1. Should have been a 1. Could have been a contender. All right, and finally, the last term has no coefficient in front of it. What? I going crazy here. I shouldn't put the f there. The f means you plug into the function, but I did plug into the function. I shouldn't also write an f there because I did plug into the function. The last one has no coefficient. 2 times 3 cubed plus 4. Like that. This is the answer of the Simpsons Rule. All right. What do you think? Any questions about that one? That's how we do Simpsons Rule. In the real world, people actually do this kind of computation in the real world. If you're doing this in the real world, you should basically always use Simpsons Rule. It's a little more complicated, the formula, but it gives you better approximations to the true area under the curve. And, of course, in the real world, people don't do this on pencil and paper. They use computers. And if you're using a computer, you might as well use Simpsons Rule. It's a more complicated formula, but it doesn't matter if you're using a computer anyway. Simpsons Rule is the way to go. All right. All right, let's just do another one. I said I had 2 examples. That was the first one, what we just did with all those parts. The second one probably will go faster because I'm not going to explain every little bit again. So second example is approximate this integral, this definite integral. The definite integral from 1 to 9, 1 over x plus ln x dx. I've heard there's some ln haters out there. I don't know how that could possibly be, but some people get nervous when they see the ln. I'm here to tell you, at least for problems like this, there's no cause for nervousness. All right, there is a ln there, but you're not going to really do anything with it. You're not going to take the derivative or take the antiderivative or anything like that. All you do is you write that as part of the function when you plug the points in. So you'll see what I mean. The ln, the fact that there's an ln there really doesn't matter at all. It doesn't make it harder or anything. That's one nice thing about these. In definite integral approximations, really what the function is doesn't really matter at all, how complicated it is. All right, and I'm going to say using, I have to tell you about the n. Let's say using n equals 4 with the same, a through e parts. So I'm going to do the left endpoints, then the right endpoints, then the midpoints, then the trapezoid, then the Simpsons. All right? All right, let's do them. So first off, right endpoints. This would be like the part A. We have to figure out what the points are that I intend to plug in. So I go, this is my interval. I just draw a simple little chart from 1 to 9, and I'm going to divide this into 4 equal parts. All right? N equals 4 refers to 4 sub-intervals. This can be slightly confusing. When I wrote these, I made 3 little marks. Don't make 4 little marks. You want to end up with 4 pieces in the end. 1, 2, 3, 4. So that's how it should work out. Any masters of common sense out there? What are these other points? Like, what's the leftmost one after the 1?
3.
Yeah, I think it's 3. I want to label these points here, and I think what you get will be 3, 5, and 7, right? If you just divide this up evenly, they end up being 3, 5, and 7. If you can't make that come together in your head, really what you need to think about is delta x is b minus a over n. In this case, that would be 9 minus 1 over 4. This is 8 over 4, which is 2, which means the width of this is 2, which is how you could figure out that first point is 3, right? Knowing what the width of each little interval is 2. Okay, anyway, I'm using the right endpoints for part A here, which are these 4 numbers, 3, 5, 7, and 9. So my answer involves plugging in 3, 5, 7, and 9 into the function that you see inside the integral sign. So what's my answer is going to be 2 on the outside. That's the delta x. And then on the inside, I plug in. I'll write it this way first. F of 3 plus f of 5 plus f of 7 plus f of 9, right? I factored the delta x out, and then I'm plugging in each of those 4 points on the right endpoints of the interval. Okay, and don't leave your answer like that. Let's actually do, what is f of 3? F means this function up here, right? That's f. So f of 3 means 1 over 3 plus ln 3 plus f of 5, 1 over 5 plus ln 5 plus f of 7, 1 over 7 plus ln 7. Finally, 1 over 9 plus ln 9. And that's the answer. All right. I hope you agree with me now what I said before about it really doesn't matter that there's a ln in there. It could be anything inside there. You wouldn't have to, no matter what it was, you wouldn't have to worry about it. You just write it again as part of your answer. All right. Any questions about that one? That was the right endpoints. Okay, let's do the left endpoints. Can someone tell me what's the difference when I do the left endpoints? I mean, I think we're experts on this already, right? We can, I think, just jump straight to the answer. What will be different about the answer?
Start with the 1.
Yeah, start with the 1 and
don't include the 9.
Yes. So I do include the 1 and I do not include the 9. That's the difference when I'm using the left endpoints. So if you like, I mean, you don't really have to write this out. Sorry. I'm using these points, right? Instead of the other ones. So I start with the 1, I end with the 7. So my answer will be 2 times 1 over 1 plus ln 1 plus 1 over 3 plus ln 3 plus 1 over 5 plus ln 5 plus 1 over 7 plus ln 7. That's it. This is the left endpoints. That's all there is to it. Any thoughts about that one? Excellent. Let's do the midpoints. The midpoints. So this one maybe bears thinking a little bit about. It's not so hard. So my original points were 1, 3, 5, 7, 9. What are the midpoints? Well, they're here, 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 and here. I don't think you have to be a master of common sense to determine. They are 2, 4, 6, and 8, right? So when I do the midpoints, those are the values that I'm going to plug in. What do we get? We get 2 on the outside. Still, the 2 on the outside, remember, is the delta x, which is still 2. These intervals have width 2. And then I go 1 over 2 plus ln 2 plus 1 over 4 plus ln 4 plus 1 over 6 plus ln 6. And finally 1 over 8 plus ln 8. That's the midpoints. Pretty good with that one. Okay, next is, how about the trapezoids? All right, trapezoid rule. This one you have to remember the formula for the trapezoid rule. It has the delta x out front, and then you use all the points, but you put a half on the first one and a half on the last one. Can you remember all that? So the trapezoid rule was same delta x on the front, or b minus a over n on the front, which in this case is 9 minus 1 over 4. And then on the inside I have a half on the first point, and then no half on the inner ones, 1/3 plus ln 3 plus 1/5 plus ln 5. And then the last one has a half on it. 1/9 plus ln 9. I'm not using the dots this time because there's only four things in there anyway, so the dots won't save you any time really. All right, that's the trapezoid rule. It's the same as the rectangle things, only you got to you use all the points, but you put halves on the front and on the end. Right? And finally, Simpsons Rule, right? And that one has a weirder formula, but you know, if you remember the formula, there's not much to it. It's b minus a over 3n, so it's 9 minus 1 over 3 times 4. And the coefficients on the inside, there's no coefficient on the first one or the last one. And then you alternate 4s and 2s on the inside of the other. So I get no coefficient on the first one, 1 over 1 plus ln 1, plus 4 on the next one, 1 over 3 plus ln 3. I'm including these parentheses because they matter when you have a coefficient. All right. Then you alternate 4s and 2s and 4s and 2s. Although I only have 4 points here. This is a little weird, but when you're doing Simpsons Rule with only 4 points, there is nothing else inside the dot, 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 right? You go immediately from the second point to the second to last point, which is why I'm using 4 both times. And then finally the last point, 1/9 plus ln 9. Right. Simpsons Rule alternates the coefficients in here, 4s and 2s, beginning with a 4 and also ending with a 4. Because we only used n equals 4, there's no 2s in this example. A little strange. But All right. Any questions about any of those? All right. That's all the example that I wanted to do today. So if that made sense, you should be good for the first first large part of the homework assignment. Really, I've only discussed the first two videos for this week. The first one was about rectangles, and the second one is about trapezoid and Simpson. The third one, the total change theorem, I will mention more tomorrow. All right. I think that does it for what I'm going to say. So I think I think we're done now. If anybody has more specific questions about the homework or anything, feel free to hang around. You know, I'm gonna have my office hours now anyway for, until 12:30. So stick around if you got questions. Otherwise, I'll see you again tomorrow.